improve. Yeah. All right. First, the question, I already described it last time. 3 rules. Yeah. So let's do the work. Okay, yeah. All right. First, analysis. How to solve this problem. Yeah. A company used the strategy that we used. For a problem relatively hard, at the beginning, we want to do some experiments. We want to get some experience. For this one, to get some experience, so usually we want to work on the simplest cases. Yeah. So when we start, we want to start with n equals 1 or 2. One trivial, right? One disk, just one move. You move the only disk to the destination peg. That's it. You're done. So trivial. So 2, but for two disks. The top one, you cannot put it on the destination peg. The top one, you like to put in a temporary tag first. Okay? Yeah. Then you move the bottom one to the destination peg. Then the top one on top of it. Following the rules. Yeah, 3 rules you have to follow. All right. So that gives you experience for n equals 2. All right. Yeah. So you get some experience. All right. Then let us work on n equals 3. Yeah. All right. Yeah. The thinking part. Yeah. So here, when n equals 3, before we work on n equals 3 directly, let us make a critical, important observation, n equals 3. Because when we work on n equals 3, we can assume that we have already solved the problem of size 2. We just did it. Whenever we need to move 2 disks, then we have the solution for it. So we just apply our existing solution on it. That view, that's the typical recursive view. Typical recursive view here. Yeah. So you need to get used to this kind of thinking, recursive view. Yeah. All right, yeah. So the size 2 problem, the solution is available, so we can apply it whenever we want. Yeah. All right. So with this view in your mind, yeah. So next, for n equals 3, yeah, because this time looks not trivial. Yeah, not trivial. Yeah. All right. Yeah. So let us do experiments. Do experiments. All right. Yeah. So let me turn off my, put in the airplane mode. Yeah. Okay. All right. Yeah. Yeah. Here, this slide. Let's do the detailed work here. At the beginning, yeah, at the beginning, very beginning, yeah. Then we start our first move. Play around. Yeah. Smallest disk, we put it on the destination peg. Yeah. You may ask why. Yeah. You may need to do a lot of experiments. Yeah. And you do a lot of adjustments. Let's assume after several rounds adjustment, we are here. Yeah. All right, so second move, the middle one we put in a temporary tag. Then move the smallest to the temporary tag. Yeah. Here you can see we just complete problem size 2 here. Problem size 2. We move top 2 disks to the temporary tag, the middle one, temporary tag. We just apply our size 2 solution to the temporary tag. Okay? Yeah. But now the bottom disk open. Yeah. Nothing on top of it. It's open, so we can move the bottom disk to the destination peg. Destination peg also empty, so we can make that move, that most important move. After that, you can see, then move the 2 disks on the temporary peg back to the destination. So we need to apply size 2 solution another time. Size 2 solution. Second time. Yeah. All right, yeah. So smallest to the starting peg, then the middle one to the destination peg, and the smallest one to the destination peg. Then we get a complete solution. So you can see after 7 moves in this order, we complete the whole solution. Yeah, that's for size 3. Yeah. When we do this solution, you can see we apply size 2 solution twice. The first time size 2 solution, and the second time, another time, size 2 solution. In the middle, between 2 size 2 solutions, in the middle, we move the largest disk from the starting peg to the destination peg. So that's our summary for this whole solution. So the solution structure is like this. But let's generalize this solution to n-disk solution. Now we're ready to move to n-disk solution. But when we make this generalization, we want to fit in the structure we just observed. That structure, apply size n-1 solutions twice. Yeah. So let me show you. Let me use the diagram, but I modify the diagram or the previous slide. So this time, let me simplify it. Yeah. Still recursive thinking. Yeah. All right. But this time, we assume size n-1 solution is available. Size n-1 solution is available. Yeah. Okay. Yeah. It's available. So we do not need to do a lot of details, right? We just take the whole solution as one step. How about that? Treat it as one step. Then we just take it. We just apply it. Yeah. So let's see. The first step, yeah. So this 3-disk, but we imagine as the n-disk stack at the beginning. Okay, yeah. We just, imagination, apply our imagination. Yeah. Then the goal, in order to solve this problem, we call it P of n problem. P of n, recursive function. We implement this P of n function recursively. Yeah. The first step, you can see, we assume P of n minus 1 is available. So we can apply that P of a minus 1 first. Yeah. Here, the temporary, that middle part, yeah, stack, yeah, here you imagine we move n minus 1 disks in a stack from starting peg to the temporary peg as a whole package this time. Whole package. That's the recursive thinking. Yep. Because this whole package, we use one recursive function call to represent it. This P of n minus 1, that is the recursive function call. Okay? We don't worry, because our high-level programming language supports the recursive function call. Yeah. So we just leave it to the computer system, language, internal system to handle it. Yeah. After that, then destination, the bottom disk to the bottom disk to the destination peg, then P of n minus 1, we apply it another time. Okay? Yeah. All right. So let me do the summary on this whole process. Yeah. The first time we apply P of n minus 1. Okay, recursive function call. Yeah. Then move disk n. Yeah, the largest one. Yeah, bottom one, disk n. Then apply P of n minus 1 again. Yeah. But there is some details. If you do the implementation, you need to specify the peg numbers. There are 3 peg numbers: starting one, temporary one, destination one. Yeah. Yeah. Because when we apply P of n minus 1 twice, those 3 pegs could be different. So you need to make some careful assignment on those 3 pegs. Then you have everything. Yeah. Then combine these 3 steps, you have P of n. How about that? P of n. That's the recursive function structure. Based on this recursive function structure, we can write pseudocode. Yeah. So next slide, the pseudocode is like this. Okay. Move disk function, void, no return. Yeah. We just do the work inside. Okay. Yeah. All right. Then 4 parameters. The first parameter, the number of disks. Yeah. Number of disks. First one, okay? Then the second parameter, from peg. So you know the meaning, right? From peg. The starting one. To peg, destination, the the third parameter. To peg, destination one, and the temporary one. Yeah. All right. So then, if the disk number is greater than 0, then we do recursion. Yeah. The body of the function. We define body of the function. All right. Move disk n minus 1, num minus 1. N minus 1, subproblem. Yeah. Recursive function call. But from peg, temporary peg, we use temporary peg as the destination peg. Then the original destination peg, we use it as the temporary peg. That arrangement. Yeah. After that, move the bottom one. So we do simulation, yeah, because in our program, we cannot really do the physical move, right? Yeah, so we do simulation, we type a message. The message, move a disk from peg number to peg, another peg number. Yeah. So this is a C++ function, yeah, because I took it from 2250, yeah, that class. Yeah. Old example you had before, yeah. So the simulation, moving the bottom disk. At the end, we apply n-1 solution another time, but at that time, temporary peg, we use it as the from peg. Destination to peg, that's our to peg. From peg, we use it as the temporary peg. Yeah. So then we complete the whole solution. Now you can see even, so here I want to show them, I want to, explain the power of recursion, because this time there are n disks, arbitrary number n disks. You move arbitrary number n disks, so you can imagine the process could be very complicated. But our code, we only need this many lines. Not many, only these small number of lines. We can do it completely. How big is the power? How big is the power? That's the reason even the recursive algorithms consumes a lot of memory resource. We don't want to drop it. We don't want to, throw it away. Yeah, because the power factor outweighs the memory resource usage factor. So we're willing to spend a little more on the resource side to get bigger power of recursion. That's the main reason. No. We enjoy the power. You can imagine without recursive implementation for this particular problem, how can you solve it? Do not use recursion. You solve the same problem. Think about it. How can you solve it? I cannot. I cannot solve without recursion. Okay? I cannot imagine how do I arrange, because you need to represent the same algorithm using for loops. So not if no recursion, you have to use for loops to do the implementation. How many for loops do you need? Think about it. Yeah. Extremely hard. Yeah. All right. Yeah. So that's this one. But at the end, I want to do another step as the summary. Yeah. Because now there is another important question we haven't answered. So that is, how many moves do we need to make to solve n disk problem? How many moves? Can I do full screen? Anyone familiar with Team? Because I'm not familiar with Team. Yeah. I will do research. Yeah. Because I want to make full screen. Yeah. Next time. Yeah. I have a student uses Teams a lot. Yeah. I will ask him. Okay. More, what's that? Yeah. Anyway, yeah. All right, yeah. So to answer this question, how many moves do we need to make? And when n equals 3, we need 7 moves. Can you connect these two numbers? 3, 7, 3. How do we get 7 from 3? Yeah? How do you get 7 from 3? If we have 10 disks, how many should be the number of moves? Yeah, that's not easy, right? Yeah. Here we need to answer that question. Yeah. Here, I just want to represent using math formulas to represent. But today, in order to save time, I do not solve it. I will leave it to another lecture to solve it. All right, let us assume the number of moves, we use C of n function. In order to count the C, we count the number of moves. In order to solve the m disk problem, we need number C of n function moves. Okay, all right. Now let us write equation. Because based on the structure, the procedure listed here, you can see the steps, key steps. All right. The first step, we need to move those number of disks corresponding to the n-1 problem. That should be C of n-1, right? Yeah. The count function, but we apply to the n-1 problem. All right. Then this one, the middle one, the bottom, plus 1. This is one move. Okay, so we count it as one move. All right, yeah. Then another C of n-1 move. Okay? That's all the moves we need. Okay, when we break down the original C function, we have another representation in these 3 steps. Now, after we combine these 3 steps, we get equation. C of n equals 2 times C of n-1 plus 1. How about that? A recurrence relation. This is a special recurrence relation. But we need an initial condition. When you solve a recurrence relation, you have to provide initial data, initial condition. Here, our initial condition, when we have one disk, we just make one move, right? Yeah. One disk, one move. Yeah, that's the initial condition. Okay, yeah. Now, this recurrence relation, pretty simple, yeah. But you need some special technique to solve it. Yeah. Let me delay it to part D. Part D, we need to solve a special type of recurrence relation. At that time, I use this example as our first experiment. Yeah. Yeah. If you want to try yourself, yeah, that's a good practice. Yeah. But there is some interesting technique we need to use. Yeah. So I delay to part D. Yeah. All right. Now, so let me move to part D topic. So variable size reduction. Yeah. So you will see when we do the problem size reduction, in our part A, we did 2 examples. In both examples, our size reduction is by 1. Factorial, we cut off one number every time by 1. The Tower of Hanoi, we reduce the disk number by 1, n-1. That's a commonly used method, but sometimes we make a problem size reduction faster, not just by 1, by many, by how many numbers that number can vary. Yeah, sometimes bigger, sometimes smaller. Yeah. B.2, variable size reduction. All right. Problem number 9, greatest common divisor problem. You're familiar with this question, right? Yeah, in the middle school. So when we start, let us start from our middle school experience. Greatest common divisor. Okay, yeah. Definition of the question. Given two non-negative integers m and n, non-negative, each one greater or equal to 0, m greater or equal to 0, n greater or equal to 0, but not both 0. This assumption. You cannot take m and m both equal to 0. Why? Because if you take both 0, the greatest common divisor function is not defined. Is not defined. No, you cannot define. Yeah. Last time, remember, when we define factorial, 0 factorial, we assume it equals 1, and this assumption is compatible with its formula, formal formula, compatible, but for this case, the greatest common divisor, if I use GCD function, now greatest common divisor, GCD, if you want to assign it a value, whatever value you assign to it, you can never get a compatible situation. You always get contradiction. You always get a contradiction. You cannot assign any valid number to it. Always wrong. Okay? Always contradiction. For that reason, we cannot assign any valid number to it. So we say not defined, no definition. Okay? Yeah. Yeah. Think about it. You think about it first. Yeah. All right. Question. Find their greatest common divisor GCD of m, n. Yeah. That's the question. Okay? Yeah. So we want to solve this question twice. Method 1, method 2. And we can learn a lot of things from these two methods. All right, so let's start the first method, the one you're familiar with. Yeah. So recall your middle school experience. You're familiar with. Yeah. Think about how do you solve this problem based on your middle school experience. Yeah, everyone has it. Here, I just recall the basic steps. All right. Middle school procedure. Step 1, find the prime factorization of m. Prime factorization. Prime, you know prime, right? 2, 3, 5, 7. So these numbers have only divisor itself and 1. Only these two divisors, itself and 1. No other divisors. So the prime numbers. Okay? Yeah. But a 1 is not a prime number. Okay? 1. Well, although it itself and a 1 itself, but only one divisor. Okay? One positive divisor. So we do not count 1 as the prime number. So the smallest prime number is 2. Yeah. So you do prime factorization. You represent m as a product of a sequence of primes. That's the first step. Second step, find the prime factorization of m. Okay? Yeah. To list of prime sequences. Step 3, find all common prime factors. Now you can compare these two sequences. You want to get the common prime factors, okay? And the greatest common factors. For each prime number, you want to extract the largest prime if we use P to represent Pi, because one of the prime numbers, Pi. You want to extract, let's say, AI, the largest possible exponent AI, such that this Pi to the AI is a common factor for both M and N. Yeah. So that's basically what do you need to do. Okay? All right. The last step, compute the product of all the common the product all in these forms. Yeah? Because we have many such forms. You multiply all of them together, that is the final number for your GCD. Yeah. Let me use example. Now here, quite abstract. Yeah. These steps, quite abstract. Let me use two concrete numbers to show you. Yeah. All right, so after that, then we do some analysis. Example, GCD of 60 and 24. First, let us do prime factorization on 60 to get the standard form. Here, you can see, when I write the prime factorization, I use some standard form. Because I can write in many different ways, right? Here, people, mathematicians, so they recommend writing in some formal form. Yeah. Here, the standard first, you look at the prime numbers. We list prime numbers in ascending order. The smallest 2, 2, 3, 5 in ascending order, not 2, 5, 3. Right? Yeah, in some arbitrary order. That's not good. In ascending order, yeah, then you organize your data well, right? Ascending order. Then for each prime number, you need to, put all that prime factor together as an exponential function. Okay? Yeah, power. Yeah. Prime to the power of some number. Yeah. That is, we call the standard form. Yeah. The standard form is important. Yeah. So you may feel just the one way to write it. Actually, it's more important than that. Why? Because if you write it as a standard form, you have a good result. That good result, we call it, there is a theorem for it. There is a theorem. Theorem in number theory. There is a big theorem in number theory. Okay? So here. That theorem is called unique prime factorization theorem. Okay? Unique. Yeah, it's unique. Yeah. Unique prime factorization theorem. Yeah. In number theory, this is one of the fundamental theorems. Many other important theorems can be proved by this one. So now you can see how important it is. Unique prime factorization theorem. All right, yeah. So then, the next question. Yeah. After we find a solution of one computing problem, here we get a solution. The next question is, Do you feel it's a good solution? Is it possible we can improve the solution? Yeah, that's another important problem we need to answer, try to find the answer. Yeah. Based on your middle school experience, this method is so easy, right? This method is very easy. The middle school kids can do it. Why it is not a good one? Why you can say it's not good enough? Right? Yeah. Prime factorization, yeah, although some of you may realize, when m and n relatively large, now, here we just consider 60, 24, relatively small numbers. So the prime factorization pretty easy. But how about n number has 10 digits, n number has 8 digits? When you do prime factorization, is it hard? It's hard, right? You agree, it's hard. But you do not really need to do by yourselves, right? You rely on computer to do it. Nobody do hand calculating on it, right? Can you apply some software to do prime factorization? Yeah, you can apply software to do prime factorization. So you may not feel it's hard, right? Yeah. But now, let me tell you, even by computer, even by software, the most powerful computation software in the world, when these two numbers are huge. How huge? Yeah, let me give you some idea. How huge? 1,000 digits number. How about that? 1,000, that big. To 1,000 digits, that big number. Can you imagine 1,000 digits, that huge? Yeah. Prime factorization on that 1,000 digit integer. This time, even you use the most powerful computer in the world, and not just the one, 100, 1,000 together. Yeah, so you can split the task, okay? Whatever you want. Still taking months or years to find the end, to do the prime factor. Months or years. Yeah, depends on your computing resource. That's slow. That's slow. Okay? Is it acceptable? Yeah. Months or years using the most powerful computer resource in the world. Google, they can use all their computers. They can afford. Still, take quite long. Yeah. Because this algorithm is not good. We don't want to add more computer resource. Yeah, enough is enough, right? Yeah, enough is enough. So what do we want to do? We want to change the algorithm, because the algorithm is too bad. The reason is the prime factorization is too hard for large numbers, for huge integers. Prime factorization extremely hard when the number is so big. Okay? Yeah. So the algorithm should not rely on prime factorization. Should avoid prime factorization, the algorithm. Okay? Yeah. Now you know why we need a second one. Why? If you need to calculate GCD function, you need to use the second one. Yeah, yes. Here, yeah, this one easy. Yeah, I just moved to the method number 2. Yeah, the method number 2, we want to avoid prime factorization. So our basic idea, reduce problem size. That's what we are learning now, right? We are learning to reduce the problem size all the time in this class. The question is how to do the size reduction. How to do the size reduction, that's the hard part. Here we need to use a mathematical tool. Mathematical tool. Yeah. Tool is important. Yeah. So what mathematical tool? Everyone knows here. In your primary school, you know it. Okay? Integer division. You know how to do integer division, right? Yeah. So let me formulate it as a theorem, integer division theorem. Okay? Yeah. It's called a division algorithm. Yeah. What's that? Given positive integers a and b, yeah, b not equal to 0, yeah, positive, yeah, yeah. All right. There exists unique integers q and r. Q for quotient, r for remainder. Q and r, quotient, remainder, such that remainder must be in this range. Greater or equal to 0, less than the divisor b, because we use b as the divisor. Strictly less than the divisor b, such that a equals b times q plus r. That's the integer division algorithm formulation. Simple, right? Yeah. Everyone knows. Yeah. You learn it in the primary school even. Yeah. But this theorem is so important in number theory. In number theory, another fundamental theorem. Yeah. Many great theorems derived from these fundamental theorems. Division algorithm. Yeah. All right. Here we apply it. Yeah. When we apply it on that GCD function, yeah, A, we can replace it by n. Our input value n. B, divisor, we replace it by n. Q and R are determined by m and n. After we do division, we will get a Q and R. Okay? Yeah. So we don't worry, Q and R. Okay? Yeah. All right. Now, yeah. Here, for simplicity, we assume m greater or equal to n and greater than 0 for simplicity. Okay? Yeah. Now we try to simplify the GCD function representation. Yeah? Using this integer division representation, m equals nq plus r. R between 0 and n, but strictly less than n. Yeah. All right, yeah. Now the simplification part. Yeah. The key property. The key property that we use for size reduction. Remember our goal, size reduction. But how? Yeah, right here. The formula to do the size reduction. We need to derive that formula. GCD formula, all right. Through transformation, formula transformation, right? Yeah. How to do it? GCD mn, we replace m by nq plus r. nq plus r. Here you can see nq term is a multiple of n. It's a multiple of n. this property is useful here. How do we use this property here? Yeah. Here, I want to show you this fraction form formula transformation. Yeah. Let's consider n over n fraction form, numerator, denominator. Yeah. And we replace m by nq plus r, but nq, you know, it's a multiple of the denominator, so we can simplify. After simplification, we get integer q plus another smaller fraction, r over n. From this one, you can see there is an integer part q plus the remaining fraction part, r over n, but you know, whatever that q number is, it won't impact the fraction part, right? Yeah. When you look at the divisor of numerator denominator, this integer part never impacts the common divisor of numerator and denominator, right? Try to observe this property. Yeah. Q equals 1, 100, whatever number it is, but the common divisor of numerator, denominator has nothing to do with it, right? Think about that. Common divisor between m and n and r and n, nothing to do with that q. Yeah. Based on this observation, we can make the simplification on this formula. That means this term can be dropped. nq is gone. Not necessary. We don't need it. When we consider greatest common divisor, that multiple term, that divisor multiple term, has nothing to do with the greatest common divisor. So it's not necessary. We can simplify it. So our simplification becomes GCD of n comma r. Do you get size reduction? After this formula transformation, do you get a size reduction? The problem size reduced. The problem size is reduced. Yeah. Here, let me just remind you, the problem size in here, the meaning is a little different. Problem size. Remember, I mentioned it before. The problem size in this question, we mean the magnitude. How large is the number? How large? The magnitude here. How about the magnitude of what, right? Because we have two numbers. The magnitude of the maximum of these two numbers. How about that? That's the problem size. The larger one. Yeah. The larger one, the magnitude, now you can see the size is reduced. How much it is reduced? Variable size reduction, right? Yeah. Because sometimes bigger, sometimes smaller. Variable size reduction. Yeah. That's the title, tells us. Variable size reduction. Okay? Yeah. All right. Then, with this simple formula, this formula is so simple, right? Yeah. But now, you can see our algorithm designed based on this formula the result. We get a big improvement as a result. Yeah. So let's see. The result is the Euclid's algorithm. Famous, Euclid's algorithm. Famous, very famous. Yeah. Yeah. More than 2,000 years, right? Yeah. The history, more than 2,000 years. Euclid's algorithm. Another important algorithm in number theory. Yeah. you're clear. Fundamental, also fundamental number theory. Okay, all right. The rule, yeah. So here, let me specify the rule when we apply Euclid's algorithm for size reduction and the recursion and the final answer. Rule, yeah. GCD of x and y, yeah. Two positive integers, yeah, yeah. Two non-negative integers, let's say that, yeah. We allow one of the two equals 0. If both 0, return some error message because the function is not defined. If both 0 xy returns error message. Yeah. If x equals 0, return, if y equals 0, return x. X is the greatest common divisor. Y is 0, yeah, then x is the greatest common divisor. All right, yeah. Yeah, because x cannot be 0 here. Yeah. X cannot be 0. Otherwise, both 0. Yeah. All right. If y not equal to 0, but x mod y, here, modulation, modular operator, x mod y equals 0. That means x is a multiple of y. Multiple of y equals 0. Then return y. Yeah. Two simple cases. Then the last one, last case, size reduction. Remainder not 0. Yeah, remainder not 0. Then GCD of y comma remainder. Yeah, because x mod y, that's the remainder. So you put the remainder there. Yeah. So it's a recursive function representation. Recursive. So you can write your code, implement this function easily, right? Yeah. Yeah. All right. And it's variable size reduction. Okay? Yeah. So so simple. Yeah. Yeah. So the algorithm is very simple here. Now, we want to see if we apply this algorithm on two huge integers, 1,000 digits. Yeah. To be fair, we can still apply on 1,000-digit integers, n and m. We do integer divisions. Integer divisions. Much faster than prime factorization. We do not need to do prime factorization. We just do integer divisions. Modulation, right? Module operation. Remainder. Very fast. Very fast. Remainder. Yeah. Integer, division, remainder, size reduction. So you flip a few times, so your computer can do very fast. Even our, PC, we can run very fast. I didn't do experiment, yeah, but it's an interesting, exercise project. If you are interested, you can try. Yeah, you can try this as an exercise project. Okay. Yeah, you use the big integer class to do it in Java or Python. Yeah, think about if you can find the greatest common divisor on 2,000-digit integers. All right. Yeah. Then, yeah, let me see. How much time do I have? Yeah, 41, so 4 minutes. Yeah. Then I just say a few more things related to prime factorization. Yeah. Prime factorization is so slow. Even the supercomputer, it takes a lot of time to do prime factorization. Is it a bad thing or good thing? Yeah. It looks like a bad thing, right? so slow. It's a bad thing, right? When you need to do the prime factorization, it takes so long, it's really bad. But can you imagine some situation that it can become a good thing? This slow computation property can be used to benefit ourselves big time. Can you imagine that? Slow is, in what situation slow is better? We know usually faster is better, right? Can you imagine some situation slower is better? The slower, the better. Encryption. Great. Encryption. You want to make hackers slower, not you slower, right? Hackers, they try to hack your, encryption code. Encryption, decryption. So there is a famous encryption algorithm is built based on this property. Difficult prime factorization, this property, there is a famous algorithm called RSA. RSA algorithm. Yeah. 3 professors, their initials, RSA. Okay? Yeah. So they use the number theory. Now, number theory, and they invented this algorithm based on number theory. Prime factorization is extremely hard. Okay? 1,000-digit prime factorization. Extremely hard. So they make the encryption based on multiplication of 2 big primes. Product of 2 big primes. So they do multiplication very fast, right? So they generate the first prime 1,000 digits, second prime another 1,000 digits, then they multiply them together, get another big number, you send that big number. But the hacker, after they receive, it's very hard to do the decomposition. They do not know how to find that 2 primes. Very hard. So that's their algorithm. Okay? All right, so let's finish right here. Yeah.